2.6. We'll talk about solving polynomial equations using graphing technology. We know that there are times that a polynomial can't be factored, and there are also times when there are no rational zeros. So even if we try the rational zeros theorem, we don't get anywhere. In that case, really technology is the only way that we have a chance of finding at least some of the zeros of the polynomial. How do you use a graph on a calculator or computer to find zeros of a polynomial? Well, we've done this before with quadratics. We know that the zeros are the same as the x-intercepts. On the graph. So wherever our polynomial happens to cross the x-axis, those are the zeros of the polynomial, or at least some of the zeros of the polynomial. Can we find all the zeros this way? Well, again, if you think back to what we did with quadratics, we saw then that only real numbers will appear on a graph. Imaginaries will not. So this method will only find real valued zeros. Imaginary zeros cannot be found using a graph. All right, so with those limitations, we still can at least sometimes come up with some of the zeros of a polynomial function. If we consider this fifth-degree polynomial, let's use a technology-generated graph. I'm going to use a calculator to find how many real zeros the polynomial has. To find out how many real zeros the polynomial has, and then we'll actually find them with the calculator. So I've got my equation in here. This is just our polynomial. That's this function. There we go. And I'm going to graph it. I think I have maybe a negative 5 to 5 on my x and a negative 10 to 10 on my y. Let's show you the window here real quick. So it looks as though we're going to find 3 zeros that are real numbers. Probably should have said 3 real zeros. Because all 3 cut through the graph, none of them have any multiplicity other than 1. They're all just multiplicity 1. So, at least most likely. If I go to my second calc and find my zeros, we'll work from left to right. I'm going to go for the first one here first, over to the left. And it's about negative 1.963 if we keep 3 decimal places. I'll do it again. We'll go with this next one. That one's about negative 1.177. And then the last one. Looks like 1.442. Those, of course, are all approximations. We've rounded them. They don't have nice, perfect fractional values. But there are the 3 real zeros that I can find on the calculator. Because, again, I kind of want to make one more mention about this all of multiplicity 1. I do believe that to be the case, although I can't be sure. I know for sure they're all odd multiplicities, but I'm not seeing those kind of funny little flattening effects that I usually see when I have a multiplicity of 3 or 5 or 7. So I do believe those are probably all multiplicity 1. If indeed we're right, and they all do have multiplicity 1, how many imaginary zeros must my polynomial have? Well, we know it's a degree 5. So there should be 5 total zeros. We found 3 real zeros, meaning it would make sense that there are 2 imaginary zeros. It was imaginary. I'm comfortable with the fact that that's an even number of imaginary zeros. They have to occur in conjugate pairs, of course, so good thing we came up with an even number. Can we find them? We really can't. Using technology, all we've got are approximate zeros. They wouldn't be enough to allow us to divide and find some kind of another polynomial, and therefore we wouldn't get the proper ones. So it's not possible for us to find them using the techniques that we know.